recall from a previous nugget that we talked about the 7 layers of the OSI model. I did mention that at the top levels of that, you don't really need to know all of the details of it on a daily basis anyway. And mostly that's going to relate to your application developer. So if you do decide to become a programmer, an application developer, a web developer, anything like that, you're probably going to be more concerned with that level. However, let's take a look again though at one of the simplified models called the actual model. And it's here that we do need to be aware of certain things. So for example, here's the model up here. You might recall that from a previous nugget. Remember that we mostly are going to be dealing with things down at this level. Okay. However, we do need to be aware of one key thing up here at this level, and that is which protocol our developers are deciding to use and which port number it's going to be used on. Okay. Now a port is simply kind of like a designated area for network traffic to come in on. So in this case, for example, we're going to start with HTTP, or Hypertext Transfer Protocol. That's normally the language of your web browsers. When they go to a website, unless it's been secured with another one called HTTPS, which I'll talk about coming up, then you're going to be using HTTP. And that's what allows your browser to read Hypertext Markup Language, or HTML. So this is an application protocol that is in use. That's why we need to know about it at this level, primarily in regards to its port number it uses, and I'll come up on that here in just a moment. But it's normally what we use for web browsing, but that's how your client will request content from a server, and again, that's normally going to be a website. So we generally use that for web browsing. Now, one thing you should keep in mind here is that this is not secure. So when you use your web browser and you access an HTTP site, then there's not going to be a little padlock in the address bar area, or depending on which browser you use, it might have some different symbol, but generally it's fairly obvious whether it's a secure site or not. In fact, there's even this website right here that I looked up, and it kind of identifies which websites are still not using HTTPS. And again, I'm getting ahead of myself a little bit here. HTTPS is just more secure. So they're basically saying which sites did not even bother to use any security on their websites, and they have a whole bunch of them that are listed down here. This was from 2018, I guess. But anyway, so they found a bunch of them, and here they are. Now, what they must have done is they must have embarrassed all these websites, because when I went to each one of these and checked them out, I didn't go to all of them, but I went to a good smattering of them. They had all gone to HTTPS by the time I looked at these, so they must have gotten embarrassed and changed their minds about what they were doing. Now, it also uses port 80, and that's going to be quite significant here if you decide to work with networks in the future. Let's explain a little bit about what this is about. So let's say that this is the internet out here, which of course, there's untrusted parties out here. You know, there's hackers, there's people that want to get your banking information, your personal identification, that kind of thing. And we also have, you know, just our office building here. And of course, like most companies these days, we go in and out of the internet. We have traffic that goes back and forth to it. What we want to do in order to protect ourselves from untrusted parties out here, and this will be somewhat true even on home networks, you probably also have a rudimentary firewall on your home networks, but we'll set up a firewall. And it doesn't necessarily look like that. It could be a physical device like that. Sometimes they are products that are installed on servers, but the main point here is this is what decides what ports to open up. So for example, if we have a website here, then we're going to want port 80 open if we don't want to use any kind of certificate on it. So then we would have to open up port 80 on our firewall to allow that traffic to come in and out. By default, firewalls normally have just about everything blocked. So all ports are blocked. Normally you only open up ports that you know for sure you actually need. So if we set up a website yesterday, we want to turn it on this morning and let people access it, somebody's going to have to tell whoever's in charge of the firewall to open up port 80. Then they'll open up that port and traffic can come on in. The general idea here is you want to open up as few ports as possible and only those that are actually needed for a business purpose. Now then, moving on, we also have HTTPS. This is going to just add security to HTTP. And what it uses originally was Secure Sockets Layer. Now it uses Transport Layer Security, which is more secure. And it uses certificates to do a couple of different things. Number one, validate identity. And this simply confirms that when we go to a website, like whatever your bank is, when you go to, I don't know, banksomething.com, that you're actually at that website and that it's not some kind of an imposter, because certainly imposters have created duplicate websites that look exactly like your own banking website, and they ask you to enter in your credentials to log on. Well, when they do that, they have now captured your username and password and could use that against you. So using certificates with HTTPS helps to mitigate that sort of a situation. And the other thing it does is to encrypt traffic. And this again would be important if we were thinking about a banking situation. So if this is our network traffic here, this is the pipe that our network traffic goes through. Somewhere in here, if we just use HTTP, for example, to send a username and password, this would be in plain text. So somebody could kind of sneak onto the wire and intercept that traffic, especially if you're on Wi-Fi. However, if you're using HTTPS, then what happens is this all gets scrambled, encrypted. And in fact, other traffic that's also on there is also encrypted and scrambled. And there's really not any way for the hacker to even know which part of this contains your username and password. And if I go to a website like I am right here at discovery.com, you can confirm whether or not it's using HTTP or HTTPS by the presence of the little padlock that we see here. Nowadays, I haven't gone to a website in a long time that uses only HTTP. Almost everything, even if it doesn't require a login, is going to use HTTPS, and you can see that there's a little padlock there that I can click on. That will help to confirm it. Notice that it does have a certificate here, which is valid. The certificate, you can think of it in our purposes right now, it's kind of like a name badge that confirms the identity. And it's mathematical, and you can even click on it and actually view that certificate here. You can look at the details of it. You can see who issued it. There are companies out there who their whole business is to issue certificates and to help with internet security and so forth. This is one of them. And you can even look at things like the certification path, which is a little bit beyond our scope, but I'll give you the idea here. Really, this can go several levels deep. And the main thing is, all the levels all the way up to the top, we have to trust all the way up through to the top. So if we trust this top level certificate in the path, then we will also trust any of the certificates that are further down the path. And the reason why they have other ones besides just the top level one is they have different reasons and different business purposes for some of these. Some certificates might only be for web browsers, some certificates might only be for email and stuff like that. And the important thing here is also that it uses port 443. Now, if you are looking forward to moving further into IT and you want to move into A+, Network Plus, maybe into Cisco, getting a CCNA, Cisco Certified Network Associate is what that means. All of those, you're going to need to know these port numbers. Okay, so if you're going to think about moving forward, I would know these. And as well for the other protocols that I'll talk about here in a couple minutes. Starting with the SMTP protocol, which is Simple Mail Transfer Protocol. This is simply the protocol that's used to send outgoing mail, and it will send it on port 587 or 465 by default. By the way, these port numbers that I've mentioned, remember HTTP was 80, HTTPS was 443, and this is 587 or 465. These are just the defaults. You can change any of those. But if you do that, it could also throw a wrench in the works because other people that are expecting to communicate with you might not know that you changed the port number, and people in the network group might need to know that they need to open up different ports on the firewall, stuff like that. So you can do it, but you just have to make sure that anybody who wants to access your services is also aware of that. And for example, here even with mail, if we decided to change these port numbers, then I would have to make sure that our IT department specified in everybody's, Microsoft Outlook or something like that, that they change to these ports when they send their outgoing mail. So for example, if we decided to change from these default port numbers to, 751 and 833 or whatever, it's just some other arbitrary port numbers, I would have to notify whoever sets up my desktop client's Microsoft Outlook, for example, to tell them to check for or to send their mail on a different port number that has to be entered into the configuration settings in the software for Outlook or whatever the email program is that they decide to use. But for our purposes, just so you know, we're going to stick with the default ones. These are other ports that I would know about. So that's on the user side. When we send outgoing mail, it goes out on these ports, one of these ports. SMTP servers will use port 25. That will be for plain text communications. Or if they are using encrypted communications, they will also use port 587. And what's an SMTP server? That's just your mail server. That's really all that is. Also, SMTP will it only transfers text. Okay, it doesn't really transfer anything but text. So if there's other content there that's not text, there's something called multi-purpose internet mail extensions, or MIME, that will help with that conversion. Now let's take a look at another thing related to email, and that would be POP3. This is used for just basic mail retrieval. It's not something that we use as much as we used to in the older days, back in early days of internet, when we had less reliable internet connections and things and modem connections. We might use this more. But the basic idea with POP3 mail, it's Post Office Protocol 3, and that's what that is. It's basic mail retrieval, and really the idea here is it only is used for downloading email. So when you make your first connection with this, it will attempt to download all emails, so you want to be well connected with it. But again, a lot of times we use this when we were on dial-up modem connections, and we rarely use those anymore. After the initial connection that you've made, then it will only catch the differences. So if I've downloaded 1,000 email messages, but in the meantime there have been 5 new email messages, in the next connection it'll only download those 5 new ones. After the download, it will then delete the email messages from the server. So this gets to be an issue, because if this is my email up here, and using POP3, I downloaded this to my phone, my smartphone, and then at a separate time, and then it will clear out all this email. There's no more email left up there anymore. And then when I reconnect in my office on my desktop computer, it's not going to see any email. All the email is going to be gone because it all got downloaded to my phone. There is an option to leave the messages on the server, but a lot of times people will forget that and really get confused here about the differences between what they would see on one computer or smart device and another. So POP3 really works best if you're only going to use email on a single device, and nowadays that's nobody. And again, it was mostly designed for kind of temporary connections. It does use port 110. Now you should still know about it, because there might be some systems that still just require port POP3 for whatever reason. You could still run into this. And it's an easy port number to remember anyway, port 110. So you'll have to open that up if you aren't a network administrator and need to make POP3 available. But this has largely been replaced by IMAP, which I'll talk about next. And IMAP is the Internet Message Access Protocol, or IMAP. This is generally going to be the preference if you have a reliable, continuous email connection, and that would be probably most of us these days. Our phones are always connected to the internet. At home, we've always got the Wi-Fi going, and it's always connected to our laptops, our tablets, our desktops, everything. Same is true in a corporate environment, because we're normally continuously connected to the internet. And the advantage of this is going to synchronize between the client and the server all the email states. So for example, here, go back again, if I've got email out here, and I've got my phone, for example, right here, and my desktop computer over here, and if I check email on my phone, and I've read 1, 2, 3 messages, those same 3 messages will appear on my desktop computer as also having been read. If I delete one of these messages on my phone, it also gets deleted on my desktop, and vice versa. And the reason why this works, and the reason why it gives us better consistency, is because the mail is really not downloaded per se to our devices. The mail really remains on the server. So really what happened here is we read 3 messages, and then we deleted one of them. Well, that's really just reading what's true on the server more than what's true on the desktop or on the phone. And that's what allows you to manage mail from multiple clients. Generally, this will use, by default, port 143 or 993 with transport layer security. This is just going to be, of course, the more secure method, but do know about both of those ports. And again, those will have to be open on your firewall. And just to give you a little bit of frame of reference for configuring this from the client side of things, this is the configuration dialog for Gmail if you check Gmail through a web browser like I usually do. Note that I can enable or disable POP right here, and I normally disable that for pretty much anything I've been using for the past several years. Notice that if I were to enable this using either one of these options, then I could keep the messages on my inbox on the server. That'll help to make it a little bit more consistent, but I guarantee you're still going to run into some problems with it. So you're better off to use IMAP if you can. Here we do see, though, that IMAP is enabled, and then we can even specify what happens if I mark a message in IMAP as deleted. It can immediately update the server so that it will also delete it from the server. You can also turn that option off, as you see. But there you have it. Those are the protocols that we will use at the application layer of our model. You do need to know the port numbers for most purposes moving forward in an IT career. I hope this has been informative for you, and I'd like to thank you for viewing. At various times throughout this course, we've talked about various types of network devices. We've talked about, for example, cable modems at other points in time. However, here I want to address these things in a little bit more specific detail and as devices on their own. And for that, let's get started here with the old crusty dial-up modem. Now, these things were really, to think about it now, it's kind of an embarrassment. They're very, very slow, and they worked with really just old telephone lines. But the basic purpose of a modem, whether it's dial-up or any other kind of a modem, is to modulate and demodulate traffic. Now, another way to, and that's what modem stands for, modulate, demodulate. But the basic idea here is you have data coming in one format. For example, over a phone line, that'll be analog, where it'll be using various wavelengths and, really various sounds to come across the wire. And when it hits our modem here, or our modem, that needs to be converted into binary, zeros and ones. So that's the purpose of a modem, is to convert telephone analog sounds to and from binary. And then that's just going this direction. Of course, we would go the opposite direction as well, to go from zeros and ones back over here to signals that a telephone line would understand. In the early days of the internet, this modem here, maybe this would be inside of your own personal computer, for example. It would be connecting somewhere across the internet or whatever to another modem. And this might be, boy, in the early days, that would be something like America Online or AOL. Wow, this is really going back a ways. But the signals had to match, so to speak. They had to be compatible. And that's a lot of times what you would hear in the early squawking phases of that. It would sound a lot like a fax machine when it's negotiating its communication protocols with the destination. Very, very similar to that kind of a sound. A lot of times on the modem, you'd have two phone ports. One would be for the actual exchange of data that I'm describing here, and the other one would be, maybe there'd be an extra port on here for an actual phone line. So you could actually pick up the phone and make calls, or it could be a fax. At a maximum, these things would support 56 kilobits per second. That's so slow, I'm not even sure what you could do with 56 kilobits per second nowadays. Any web page you load at 56K would just barely load at all. It'd be very, very slow and frustrating. And that's basically what we had back in the old days. By the way, this was also a theoretical maximum. Usually it was much, much slower than that, usually around 33 kilobits per second. So I'm going to quickly move on from that because, and then for visual reference, I just did a Google search for dial-up modem, and I had a few of these. It's kind of embarrassing to look at them now. I had this one right here, that old US Robotics one. But generally, they would usually look something like this one right here. If I just magnify that one from BH Photo, you can see it had an inbound port to come in from your telephone service provider. That would be your analog signals coming in. And then it would be converted somewhere within the circuitry of this thing into binary. And then it would go out the modem in a binary format. And then here would be your other line for fax or another voice machine. And then here would be another port for your phone line, so you could use it for voice or for fax. Now, thankfully, we've moved on from the dial-up modem. Some places will still use these as a last-ditch, rudimentary effort to keep some kind of connectivity in the event that all other internet access or all other links go down. This could be used, for example, for a point-to-point link between two sites, between two networks, but just avoid it. Try not to use this at all if you don't have to. The better solution nowadays for home office, small office, home office especially, would be a cable modem. With a cable modem, what we're doing is we're converting cable analog coax signals. Again, we have this thing where we have, this kind of a wavelength type of a signal that's coming across the wire, and we need to convert that in our cable modem to digital signals, zeros and ones, so that our computer and other network equipment can understand it. There are several different standards for this. The current one as of this recording is something we call a DOCSIS. This is a standard that's used 3.1, and that would give you theoretical speeds up to 10 gigabits per second, but I don't know of any small office, home office ISPs that support 10 gigabits per second. Most of them right now are going to be somewhere in the 1 gigabit per second range. Again, as of this recording. Also, you can buy or rent these from your ISP, or if you can buy them from anywhere. You can buy a cable modem from Amazon, for example. That's where I've got the last couple that I bought. But you can also rent them from your ISP. That way you don't have the larger upfront expense. And they're, $100, $200, depending on which one you get. But if you just want to pay for it on a monthly basis, you can. The only advantage to that is the support of that cable modem will be borne upon that ISP. So if something goes wrong with it, it's on them, and they have to replace it. Whereas if I bought it and something goes wrong, it burns out, whatever, then I just have to buy another one. Also, if you lease one or rent one from your ISP, then you could probably also get free upgrades. So if there turns out to be an upgraded one, you don't want the one you've got anymore, just take it back and get the newest one. Usually, it's just on a month-to-month basis. You're not obligated, like in an apartment lease where you have to be obligated to that thing for a year or something like that. And now let's move on to a router. And trust me, it's a router, not a router. That's what amateurs call these things, okay? All right, so it's a router. Anyway, what does a router do? Well, it directs traffic from one network to another at its most basic format. However, as we take a look here, I'm going to be describing this mostly in a small office, home use type of an environment where it really duplicates a lot of the functions of a firewall as well. So a lot of times these terms and these descriptions kind of overlap or get a little bit fuzzy, but let's describe what it does. Basically, it'll allow open ports for various types of services. So if you're an online gamer, you might have certain ports open for certain gaming services so that you can communicate back and forth with other gaming servers. But for small office and home use, we don't really have a lot open. And generally, there are very few ports that are open inbound, and generally it's broad outbound. In terms of the physical nature of these devices, for again, a small office, so at home, these are going to usually have one external port that's coming in from the internet, but it could be called an external port, it could be called the internet port. On some devices, it'll simply be labeled as the WAN port, but for most of our purposes, that's just going to really all be internet. And then we'll have internal, multiple switched LAN ports. So if I kind of draw this out, we might have a router here with a port. That's an RJ45 jack usually that connects ultimately somehow. Could go through a cable modem and other network equipment, but ultimately it'll be out here, let's say, to the internet. And then there may be internally multiple switched ports. They'll look the same. Might have different color on them just to make it clear to the user. But these will all be ports to internal devices, and let's just make all of these, computers. Some of these will only have one that goes out to the internet and only one, let's ignore these, that comes in, and then that would in turn probably connect also to another switch of some kind with additional ports on it that we could then connect our various other computers and devices to. Now, one of these may also be connected not to a computer or a device of that type. It might in turn be connected to something like a Wi-Fi access point, which we'll talk about again also coming up. So again, it could connect to, like I said, one port that connects in turn to other equipment. These at a home or small office, home office level will also often include something like parental controls. So it'll block certain naughty websites and things like that, and of course your teenagers will figure out how to get around that in about 30 seconds. Now on a corporate level, a router usually is truly a router. They're often more dedicated, true routers, and they're very often closely associated with firewalls, intrusion prevention systems, intrusion detection systems, and some other things which I'll talk about here again coming up in more detail. But remember, on a kind of a more corporate level, a router, if I just draw in a symbol for one, which is usually these 4 arrows in a circle, the main job of it is just to redirect traffic to some other location, okay? It could be a WAN link to another office, it could be to the internet, it could be to another floor within my same company, but it's usually going to direct traffic either to an ultimate destination or really to other routers in turn. And then let's move on to the switch. Now remember, at the switch level, we're really dealing with LAN traffic. We talked about this when we talked about the layers of the OSI model, and we talked about layers of network traffic. Remember, there's the physical layer down at the bottom, and then above that is the data link layer. These work at the data link layer, and so what they want to do is to direct traffic to specific MAC addresses. Remember, each port has kind of a memorized MAC address. Whatever's on the other end of that port on a switch will be, normally it's going to be a computer, a desktop computer, whatever it is, and it will have advertised back to the switch what its machine address is, or its MAC address. And so the switch will communicate at a binary level through that port. Now, ports are generally designed to be extremely fast. On switches, we really, really want them to be fast. We have a lot of intercommunication going on between these various ports, especially on a corporate level, but on a small office, home office level, they can also be very, very simple. I've got a 24-port switch in my own home office here that's behind an access panel, and it's just got a whole bunch of RJ45 jacks in it. It's double stacked, and there's 24 of these things, and they just connect Ethernet connections throughout my home. When my house was being built, I just kind of evaded the security guard that was patrolling the neighborhood every night, and I came in and I strung a bunch of Ethernet cabling all through the walls before they put the drywall in, and then I ultimately terminated it all at this access point here where I have this switch. The ultimate end to that being that I can have fast Ethernet connection in just about every room of my house. But that's at the small office, home office level. This is kind of a corporate idea that we have here. For most of us, in a small office, home office environment, we've probably got a switch with maybe 4 ports, 4 or 6 ports on it, sometimes 8. And this might be for a cubicle connection where we have a small office and we got a few co-workers all connected together here. On a corporate level, this can be very large and have a lot of flexibility and configurability. You can do a lot of things with this. You can have VLANs, for example. So, for example, maybe you could split these up into their own separate network. It would be a separate, what we call a broadcast domain. And it's really way beyond what we need to do. But you can think of that as a whole other network. You can have dozens of these ports. A lot of the switches will have 48 ports. And then, if that's not enough, you uplink it to other devices. And so for this, I thought the best thing to do would be to just take you to Cisco's website. And you can see that's where I am right up here. The Catalyst 9200 is a common switch. This, I'm pretty sure this is a 48-port switch. It looks like it is. And this can be used a lot of different ways. Okay, so first of all, I can connect, let's say, 48 hardwired Ethernet connections onto this. Or I could even use one of these to connect to, ultimately, maybe some other kind of an access point for wireless, which we'll talk about here also coming up. And if 48's not enough, I can just stack that on top of another one and just duplicate this and have another 48-port switch underneath here. And then I can kind of connect these two together, and now I have 96. And if that's not enough, you just keep on going and adding more switches. And it must be good. Look, it's got 4.5 stars. And then we move on to the access point. This is also known as just a wireless access point, WAP, wireless access point. This is generally used for internet and LAN access. These will usually have a single Ethernet connection that comes in usually from something like a cable modem or from some other network source. And then the access point becomes your availability point for your internet and LAN connectivity to any devices that connect to it. These are often also divisible into multiple service set identifiers. We haven't really talked about that yet, but an SSID is just what you see when you're, for example, using your phone and you're at a restaurant and you're trying to find their Wi-Fi. Whatever the name comes up as, Billy Joe Jim Bob's Cafe or whatever, that's the SSID. That's how it's identifying that wireless access point. I'll get into more detail in this when we talk about the wireless skill coming up. And so the access points, they're very often like this on a corporate level. You'll probably see these in many office buildings, restaurants, places like that. These are usually up in the ceiling. It looks a little bit like a smoke detector. Maybe they should combine the two into one, save a little bit of money or something. Anyway, so that's a lot of times you'll see on a corporate level. But on the consumer level, you'll see it look a little bit more like something like this a lot of times, where it'll have antennas on it. It's combined with a switch. You can see back here, these are all switched ports. This is the inbound from my cable modem usually. I think this is the actual one that I have in my office, by the way. And also be aware of the fact that nowadays, a lot of these devices can be combined into one. So, not just talking about access points, but you can combine, for example, the cable modem could also be your router, and it could also be a switch, and it could also be a wireless access point, and there might even be a telephone line on it. In fact, I think my own cable modem now that I just recently got has all of those things integrated into it at once. So it's kind of a one-size-fits-all thing. And that might be very useful if you need to consolidate and you're limited on space. You don't want to have a whole lot of cables going all different places and stuff like that. And you have maybe even limited power outlets. Otherwise, you'd have to plug in a separate power outlet for each one of these things. And here I just decided to go to, Cox's own website here. I think this is the actual one that I have. And you can see here, it's got a lot on it. It doesn't look like a Wi-Fi thing, but it really is. A port here, one for 2 telephone lines, if you wanted to use them. It's got 2 Ethernet ports here, and one of these could connect to another switch, for example, or directly to your computer. And then here's where it would come in using coax from the street. Here, of course, is my power connection. And inside of that would be the routing and firewall services that I would also get from Cox. So again, you can kind of see here where they're really just putting everything into a single box right now. It makes it pretty convenient. Now let's talk about a firewall. A firewall might be integrated into something like that device I just showed you, but at the earliest levels of this, a firewall was really just a port blocker. I talked about that, I think, in the last nugget, where if we only wanted to allow inbound traffic to our website here, we would only open port 80 or 443 or both. And other than that, all ports would be blocked. Well, firewalls are much more sophisticated than that these days. But at the beginning level, at least, they will still allow inbound and or outbound ports. These firewalls can be hardware and or software. Usually it's some combination of the two. And these are just another type of what we call a network appliance. And a network appliance is just kind of a general term nowadays for anything that handles stuff on the network. There's so many different types of network appliances, switches, routers, firewalls, and so forth, that are kind of generally called a network appliance, which would be a kind of a dedicated device for the network, but it may also be a server, which has some kind of a rudimentary, at least, UI with firewall software on it. So it might actually be a computer instead of a network appliance. With a small office, home office environment, this is often going to be integrated into the cable modem, just like what I showed you just a moment ago. That Technicolor, I think it was called a Technicolor device that I showed you, the one that I actually used, a couple times a week, it'll actually alert me that there's been an attempted hack into my network, and it usually, honestly, comes from a Russian IP address. I don't know why. I've got a lot of friends in Russia. I don't know what they're trying to do to me. Anyway, in the corporation, they're usually not kind of one-size-fits-all devices. They're usually dedicated solutions. And we've got a lot of training here on firewalls and so forth at CBT Nuggets. It's a pretty fascinating topic on its own. These will often involve artificial intelligence and machine learning, which means kind of like on the fly, these things can just intelligently detect that incoming traffic is probably malicious, and it can be compared to other malicious traffic that looks similar, for example. These are also often combined with intrusion detection systems and intrusion prevention systems. You don't need to know that for IT fundamentals. I'm just letting you know that that's kind of another whole arena here. And they're very, very effective solutions at blocking that sort of stuff. And they'll often detect things, like I was saying earlier, known malicious IP addresses, like my friends, so to speak, from Russia, virus signatures, traffic that just looks kind of fishy, and denial of service attacks. You don't really see that on the home office level, but on the corporate level, you'll see that all the time, where the attempt is that we just want to, if you're a hacker, you just want to bring down a server. So if you think about going to the post office or someplace where there's a large queue, a large line, and you have to go up to the little tape machine, you have to pull off a number, take a number here, it says, just imagine everybody with those numbers rushing the counter at one time and saying, serve me next. Okay, that would overwhelm the clerk, and that certainly overwhelms various types of devices. That's called a denial of service, where we're just trying to overwhelm a certain type of a service. So by way of example, I've gone to Check Point's website here, and they are a very well-known firewall technologies firm. They have excellent management software as well as hardware devices. And you can see that these look a lot like routers or switches. That's because they kind of combine that too. And I'm attempting to zoom in here so we can see better, because these are black, it's kind of hard to see. But anyway, you can see a lot of switch ports in here, as well as what's probably inbound ports from internet service providers. And some of these ports are modular in the sense that you can plug in a certain module that will be able to use fiber or some other inbound medium. Now, granted, that all is a little bit beyond our scope here. We're not really talking too much on the corporate level here, but just wanted you to be aware of what's available there. And these things are just fascinating. Can't even go into it. All right, that's all we have time for here. I hope this has been informative for you, and I'd like to thank you for viewing. All right, so we've covered quite a lot of material about networking in the past few nuggets here. So let's go ahead and address these in a pop quiz. Don't you just love pop quizzes? I'll bet you love to hear that phrase when you were in school. Today we have a pop quiz. Well, here it is. Pop quiz question number 1. Which of the following characterize a WAN? And like I did, I think, in the last pop quiz, I'm going to give you about 3 seconds of just empty dead air here so that you can think about it. And it also gives you time to hit the pause button so you can take a little bit more time if you need it. And then when we're done with the 3-second pause, I'll resume. All right, so as we take a look at this, remember we have a couple of different kinds of networks here, major networks. One's a LAN. There's other types as well. There's a LAN and there's a WAN. We're talking about a WAN here. Wide area network should be kind of one of the clues there. So we know that it's going to be physically distant. And we also know that to connect physically distant networks, You can't do it with some of the other items we talked about in networking, like a switch. That's for a LAN, remember. So that's not going to be a good answer. But they are going to be distantly connected, so that's going to be connected by routers. And we know that they are not physically close, so obviously this wouldn't be right either. So our answers there are going to be A and B. Pop quiz question number 2. All right. Which of the following, you're gonna have to have more than 3 seconds for this one. I think I'll need more than 3 seconds for this one. Which of the following are correct protocol and port numbers? Now, granted, this one's gonna require a few more brain cells. You're gonna have to have a little better memory, or you might need to review the material a little bit where I talked about these things. But the basic idea here is I only want you to pick the answers that have the correct port number next to the protocol. All right, so let's take a look at this. Now, the first thing I'm going to do is to clearly mark off the ones that are not correct. So that's clearly just not correct. That's just wrong answer. This one, however, is POP3 does use port 110. So that is a correct answer here. I can't seem to make a check mark. There we go. HTTP does not use port 75, so that's not correct. SMTP does use ports 25 and 587, so that would be a correct answer. HTTP does use port 80, so that's a correct answer. SMTP does not use port 993, so that's not a correct answer. IMAP does not use 222 or 666. I don't know. Oh, but that would be a real evil port, apparently. And then port 3. Oh my goodness. POP3 does not use port 25. HTTPS does use port 443. And IMAP does use port 143 or 993. And also, as a quick side note here, these are all what we call TCP ports. If you remember from the discussion we had on TCP as opposed to UDP, these are ports that are going to be using TCP. So all of these would require, like traffic confirmation and to confirm that each packet gets there and so forth. But the reason why I emphasize that is because if you don't specify whether it's TCP port or a UDP port, then it's usually a TCP port. Okay, it's just by inference. There are also UDP ports, which we don't really discuss in any of the requirements here for the IT fundamentals exam, but they do exist. So there's UDP port numbers for various other services and protocols. Pop quiz question number 3. Which of the following are common small office, home office, network devices? All right, let's take a look at these. One of those would be really a cable modem, okay? You got to have that to get internet, right? Then we have, once we receive the internet, we have to route it to our internal network. So a router is a good answer there. We want to secure it with a firewall. We usually, on these routers that we have in answer B here, there's usually several ports that are connected by a switch. It's really a switch. And then there's also access points, which are very common in home networks these days. Remember, a lot of these can be combined into a single unit. So really the answer here is F, all of the above. All right, pop quiz question number 4. Which of the following describes a MAC address? It's a unique 32-bit binary number. No. There is something else that is a unique 32 binary number on a network, and that would be an IP address. Remember, zeros and ones, they all add up to a certain kind of a combination of numbers in decimal. Well, that would be something like an IP address, so that's not correct. A MAC address is not a port number associated with a specific service either. It is a hex value that uniquely identifies a network interface. Sometimes, by the way, you may hear this also referred to as a hardware ID. But that's what it is. It's answer number C, and of course D would not be true. So your correct answer is C. All right, pop quiz question number 5. Which of the following are relevant at the network layer? Remember, this is where we discussed the various network layers. Start with the OSI model. Presentation layer, data link layer, network layer, transportation layer, session layer. You go up the stack and so forth, and the application layer. But there's other simpler models. We used what we call the actual model there. And at the network layer, if you recall, it used a specific kind of hardware device to handle a specific kind of address. So let's take a look here. Switches, remember, those operate in a different layer. Those are going to be at the data link layer, and they handle the MAC addresses, remember. Routers do work at the network layer, so that's a correct answer. And routers route based upon IP addresses. So that is a correct answer. We already established that MAC addresses is on a different level, so a different layer, so that's not correct. And protocols and port numbers is also not on the network layer, at least where that determination is made. So your correct answer here is answer B and C. All right, I think this is the last one. Pop quiz question number 6. Which of the following describes the role of a DNS server? All right, so remember, a DNS server is going to convert something for us, is going to resolve something for us, all right? Let's just start at the bottom here. Does it retain a database of MAC to IP address mappings? No. But for bonus pop quiz credit, do you remember which device it is that maintains the MAC to IP address mappings? Remember, sends out an ARP broadcast to find out which network device has a specific IP address, but it's looking for the MAC address, right? So that would be a switch, all right? And then let's look at this next one, answer number C. Automatically issues an IP address to a client. Well, there is a server that does that, but it's not a DNS server. It's a DHCP server. DHCP. Stands for Dynamic Host Configuration Protocol, and you don't need to know that for the exam. I'm just letting you know that right here. Converts IP addresses into MAC addresses. Nope, that's just not correct, but it does resolve a name to IP address. So, for example, if you type in your browser www.cbtnuggets, because that's where everybody wants to go, then in the background, and you're not really even aware of it in a practical daily sense, it actually converts that into an IP address using a DNS server, and then it goes to the proper IP address over the internet to get you this wonderful video. All right, that's it for this nugget, and that's the end of your pop quiz. I hope this has been informative for you, and I'd like to thank you for viewing. Wireless radio frequencies. Wow, what a concept. I mean, there's billions of wireless radio signals emanating through the airwaves constantly, day and night, penetrating through our brains and so forth. Okay. Whew, ow, a little bit scary, isn't it? Well, let's take a look, though, at what's there. Let's take a look at how many times per second something is penetrating our brains that's not our own thoughts. That would be these wireless radio frequencies. And really, of course, I'm kind of being a little bit facetious, but the idea here is we want to be able to use these to perform network communications. And back in, I guess it was about 1999, is when all of this stuff really started coming onto the scene. And we were able to start using, instead of wired networks, where we always had to have an Ethernet cable connected to something, now we're able to actually use wireless starting back then, okay? Now, it started off a little bit rocky because there were some problems with security, and there still are sometimes. However, they have improved. Let's take a look, though, at what we really have here. With these wireless radio frequencies, there's two common standards. Well, the first one is the 2.4 gigahertz range. Actually, there's 3 now, but there's 2 in common use. And this is, the 2.4 gigahertz means that there's a frequency. A frequency means how many times something cycles, like up and down, right? So these radio frequencies will cycle 2.4 billion times per second. That's what the gigahertz means there. Okay, so, you know, again, you have these radio frequencies here, and these are all radio, right? And so it could be that, you know, up is 1 and down is 0. Remember that ultimately, on the network level, when you get down to the physical level and actually getting data to a network card, and it could be a wireless network card that's receiving or sending this data, then it's going to be ultimately binary, okay? So it has to get to 1s and 0s. And the 2.4 billion simply means that it makes this, you know, up and down cycle 2.4 billion times in a second. Wow, it's amazing. That's a lot, isn't it? Now, we're going to see a little bit later on here that doesn't actually seem to be ideal. There seems to be a better standard than this 2.4 gigahertz, but it was the first to market. Actually, the 2.4 gigahertz and the 5 gigahertz both came out in about 1999. But the problem here is that the 2.4 gigahertz circuits, and I guess the availability of the integrated circuits that made this available in various radios was more broadly available, so it kind of won the market. So it also does give a further reach than 5 gigahertz, okay, which was the other standard, and we'll talk about that more here coming up. And it also provides better penetration of obstacles. So, for example, if you've got an access point right here, and here's where your desktop computer or your laptop is over here. And in the meantime, this is trying to communicate with my wireless card in my laptop, which, by the way, those usually go around the circumference of the screen on laptops. That gives it a broad, wide surface with which to send and receive signals. Anyway, here it might have to go through a brick wall, okay? And when it goes through that, it's gonna become a weaker signal as it goes. If it can even penetrate it. It kind of depends upon the materials that are there and so forth. And then it might go through some studs over here with drywall. And then maybe you're in a fancy office environment where you have this big glass wall with, the big block of glass that goes through here. Well, glass is actually a big significant blocker, if you will, of radio signals. We don't think of it that way because we think, well, it's just glass, I can see right through it. But radio signals actually have a little bit more of a problem getting through that stuff. So anyway, by the time you get through all of these walls and things, your signal might be really, really tiny and weak. And when you look at the wireless access points that are available to you, this one here might look like it's very, very weak. Now then, erasing all of that stuff, let's just take a look at another factor here as well. Sometimes the power of these things, of these wireless access points, is quite high. On the more advanced ones, you can actually adjust the power level that they emit. So if someone's got this thing cranked up and it's going way, way, way out here, and a lot of the consumer level ones are always on maximum. Because for marketing purposes, Linksys or Netgear or whoever the company is, they want their access points to look like they're the most powerful ones out there, and you can always get a great signal. Well, it's going to look like, you might be able to. Let's say that these are probably, fairly physically distant, and maybe there are some obstacles in the way and everything, but as it's emitting its signal here, on my laptop, it looks like, wow, that's got whatever bars, 5 bars or whatever, and it looks like it's really strong. So I want to select that one, because I want the fastest Wi-Fi possible, and the strongest signal possible. The reality is, however, the Wi-Fi antenna here, it only gets so much power. And the laptop manufacturers, one of the big selling points of them is how long the battery life is on these devices. So if they send too much power to that antenna, then they're going to wind up depleting the battery faster, and they have to think about that. Other things are factors there as well, the CPU and, the usage of the laptop and all. But so what we might see happening here is this looks like it's full power, and we want all the bars, so we select that one. Problem is, when we're trying to send data back, our signal might be weak, so we might kind of peter out, so to speak, by the time we get here. And we might have something that has 5 bars, but we're not getting a very good throughput of data through it. And we kind of wonder why that might be. I just want you to be aware of the facts, some of these things that could come up. So in other words, to summarize that, we have super powerful strength coming this way and really, really tiny power going back this way. And maybe we can barely reach it by the time it gets to there. And obviously, that's going to really affect our overall throughput. Now, as I kind of illustrated there, it has the lowest bandwidth in terms of the wavelength, the lower frequency and everything, and the lower bandwidth according to the 802.11 standards, which we'll look at later. See, there are network standards that start with 802.11, and then there's a letter here, A, B, C, A, B, there's not a C, but there's an A, and B, and N, and some others. Well, a couple of the earlier ones especially would use this 2.4 gigahertz range, primarily because it was just available and it became kind of ubiquitous early on in the Wi-Fi battle. Here we kind of have the battle of the bands where we have 2.4 gigahertz and 5 gigahertz, which is coming up here. But many other devices also use this space, and so that's something else to think about as well. So again, if I have my access point here, and it's emanating out its signals, trying to reach my, my laptop over here, in between, there might actually be some other things going on here. I might have a phone here that uses 2.4 gigahertz. Maybe we have to communicate through the break room, and we have, several microwaves going on here. For some reason, at lunchtime every day, we seem to lose our wireless signal. That's because these microwaves are sending out signals and interfering with our communication. So by the time it hits these microwaves and goes across these cordless phones and everything, we have frequent interruptions in our wireless signal here. Now, as far as the user experience of that will go, that's probably going to just mean that there's a lot of retransmissions. And that's just, from their experience, it's just going to be slowed down significantly when it has to compete with these cordless phones and these microwaves, for example. And in fact, I ran into that in my own home. I was an earlier adopter of Wi-Fi years ago. I had a 2.4 gigahertz access point, and we had a landline back then, but it used the cordless phone, which we thought then that was, state of the art, that you have a cordless phone, that you don't have to get tangled up in the cord. Well, anytime my wife would be on the phone, it turned out I would get kicked off the network. I would get kicked off of the Wi-Fi because they had overlapping signals. Some cameras may also use this 2.4 gigahertz range. Another 2.4 gigahertz range overall is largely being replaced for more modern alternatives, but you still have a lot of those 2.4 gigahertz network cards and access points that are installed out there. And when you think about a large company with tens of thousands, maybe even hundreds of thousands of users and devices out there, to replace all of those access points, that's a multi-million-dollar expense that they have to weigh against and consider whether or not that's worth it. But almost any new installation of devices is going to be using more modern 5 gigahertz frequency range, which of course would be 5 billion frequencies per second. So if this looked something like this, this is not all to scale, by the way, just so you know, this is going to look a little bit more frequent, just about twice as frequent, right? Now, because it's a higher frequency, that means we get our ones and our zeros faster than we do on this one. As a result, we should be able to get better speed out of it. And we are. We're going to get higher bandwidth, but this frequency range right here, for whatever reason, it has more trouble with obstacles and interference, so it has a shorter range than what we'll get out of this guy up here. And it's a little bit difficult to quantify sometimes, because you have to only, test these things. If you really want to test these things scientifically, you pretty much have to test them in a vacuum with no obstacles between the sender and the receiver and so forth. But in the real world, every house is different. Every office building is different. Everybody has a different number of microwaves that are in the way. All that sort of thing. And by the way, some cordless phones were also using the 5 gigahertz range here as well. But there's not as many other electronic devices that might use that same range. Nevertheless, again, it still has more trouble with obstacles, and it just has a shorter range by its own nature. So even in a perfect environment, this is still going to be shorter than this one in a perfect environment. And just kind of for giggles, I've brought you here to the United States frequency allocations. This comes from the United States Department of Commerce. And I can't even read this because it's so small, but I think it's over here somewhere. Is the 2.4 gigahertz? It's down in here somewhere. It's this tiny little range of radio frequencies that can be used. And then, of course, 5 gigahertz would also be, somewhere over here as well, I guess. Because this is 3 gigahertz and this is 300 megahertz. So anyway, somewhere in there is that range. And look at all these radio signals. Oh my goodness. The United States government would like me to inform you that there's no concern for having all these radio signals beam through your body day and night. Now, also, the United States government would like me to inform you that despite the fact that there are probably trillions of various wavelengths beaming through your brain at all times of the day and night, there's really nothing to be concerned about here at all, folks. Nothing at all. All right, in our next nugget, we're going to talk more about Wi-Fi here and the various radio frequencies. I hope this has been informative for you, and I'd like to thank you for viewing. I remember when I was younger, I would move across country in my little Ford Pinto, a 1972 Ford Pinto. And as I was going across country, I would want to tune in radio stations. So it wasn't the digital ones like we have now where you can choose exactly 101.5 or something like that. Instead, you had to turn a little dial until you could kind of hear a radio station, and then you'd kind of go over a little bit, and then you'd go back to what you felt like was the strongest point of the signal. And then as you would go across country, and that signal would get weaker and weaker, there might be another one that kind of overlapped it. And then sometimes you kind of hear two radio stations talking at the same time or playing music at the same time, and it's really irritating. But that's what happened when we would have two signals that overlapped one another. And guess what? We still have that problem today. But it's not in radio signals that we use for entertainment purposes. It's radio signals that we use for networking, and that's a problem. So in an upcoming nugget, I'm going to show you how to configure an access point. The access point has to have a specific channel number. Just like you tune a radio on your car to a certain channel, you also have to have a similar thing here with an access point. They really are, after all, radio signals. So what we want to do, though, is to configure two radio signals so that they don't overlap or conflict with each other, all right? Otherwise, you have the same kind of thing that I had in my car. We have two radio stations playing at the same time. So let's say that somebody does not know what they're doing, and they know they have to set up 3 access points in their building. Maybe they have a human resources department that needs Wi-Fi, an admin department, and maybe IT. After all, we're on the bleeding edge, so we have to have Wi-Fi as well. So they say, let's give HR channel number 3. And let's give admin, let's just go sequentially here, number 4. And let's give IT channel number 5. Well, it sounds like a great idea, doesn't it? After all, these are not the same channel. You're supposed to not assign 2 of these the same channel, let's say, for separate access points. Now, this does create a problem, though. Let's take a look at this. Let's look at the middle one, number 4. Look at the dotted line here in the address space that it uses, or in the radio space that it uses here. This is kind of the reach of that. Notice that for these channels, they're all 2.4, but none of them are exactly 2.4. Number 1 is 2.412, 2 is 2.417, 3 is 2.422, and so forth. So we're kind of getting that thing where we twist the dial just a little bit, and we're kind of getting part of another radio station in there. That's what happens with this as well. Look at channel 3 and what its space is. Okay, it goes from here over to here. Do you see a problem here? Yeah. There's all this overlap. Channel 3 and channel 4 interfere a lot. In fact, they only have this little sliver of space on both sides where there's a clear channel. And that's not even that great either. Why? Because look at channel number 5. I can't even draw that one. That one goes over here as well. And so channel 5 also overlaps with channel 4, so this space is all messy. And we've only got this much space in channels 5. So what's the moral of the story here? Is it that you cannot use Wi-Fi? You can't use the 2.4 gigahertz range? No, you can. You just have to be careful about how you separate. See, what happens here is when they have these conflicting spaces in here, maybe I've got a laptop that's kind of halfway between access point that's using number 3 and halfway between access point that's using number 4, then I'm going to get all of this interference. My Wi-Fi signals are going to have collisions, they're going to have retransmissions, and I might have 5 bars for the access point that I'm connecting to on channel 3, and I think I should get great signal and great throughput and speed, but the reality is because it's retransmitting and colliding a lot with the other channel that I'm going to have very slow speed. Likewise, though, a friend of mine might be over here in this department and they're on the edge of 5 and they're only getting, 2 bars, okay? So they don't look as strong as me, but over here they don't have any interference if they're on this far edge of that access point. So even though they're getting fewer bars in their signal strength, they might be getting a lot better network performance than me, and they're able to watch YouTube all day, and I have to suffer through it, skipping and jumping all the time and not getting any good performance out of it. My email messages with attachments send really, really slow, and sometimes they don't even make it. His email attachments over here, he seems to do great with only 2 bars. And that discrepancy is, again, because of all this mess that we have in the middle with the overlapping channels. So, how do we do this and keep everything real clean? The general rule of thumb is you want 5 channels of separation between your channels. So, we would choose channel number 1, and then up 5 channels would be number 6, and then up 5 more would be channel number 11. And theoretically, if you had, not all access points have up to channel 14, but theoretically, if you had a 12 and a 13 and a 14, you could also use one of those, not all of them, because then again you have overlapping. But if you could use 1, 6, and any one from 11, 12, 13, and 14. Then notice that we don't have any overlap. This one goes down to here, this one goes down to here. We don't have any overlapping problems. By the way, in case you're wondering, again, these are going to be access points that are probably in the ceiling. They might have antennas on them. And they are all configured with a different channel. So this is channel 1, this is channel 6, this is channel 11. But if I'm on a laptop, and let's say I start right here, and I happen to be right underneath this access point on my laptop here, I'm going to get great signal out of channel 1 on that access point. But to me, it's transparent. If I take my laptop over to the conference room that's right under the access point number 6, it switches me over here transparently in terms of what the user experience is. But as far as the user is concerned, they don't have to do anything. And then when I go over here, and I'm working out of the break room, underneath access point with channel number 11 on it, again, I have a transparent and good, clean experience here with no dirty signals. The only thing that the client knows, and some administrators like you and I might configure this for the user, is that we would configure their Wi-Fi to connect to a certain service set identifier, which I'll again cover in more detail later on. But maybe the name of our Wi-Fi in our network is Corp Wi-Fi or something like that. So we'll just connect to that. All of these access points will have the same name but different channels, and that's why I'm able to roam from one part of the building to the next. Looking at that another way, maybe I would have my, if we look at this in a diagram with a blueprint, maybe I'd have access point number 1 right here. Maybe in the middle I'd have number 6. Maybe over here in the far corner I'd have number 11. If you take a look at the 5 gigahertz range, which we have right here, Notice that we've got a lot more selection. These are the channels right here. It starts at 36 right here, goes up to 181. And so just because of the fact that there's more selection there, and remember, the 5 gigahertz range has a shorter range. So it doesn't have as much distance to reach out and potentially overlap with a neighbor in the first place. But because there's more choices, we don't have as many problems with this. Also, by the way, many of the more modern access points will have an automated setting where they'll be able to detect interference with other channels and auto-select the cleanest one. Now, also in the 5 gigahertz range, and by the way, this is gigahertz. Look at this. It says 5,250 megahertz. Remember, 1,000 megahertz equals a gigahertz, so that's actually 5.25 gigahertz, just so we're clear on that. But anyway, we have other capabilities within the 5 gigahertz range as well. We have something called channel bonding that can take place. So for example, we're at the 20 megahertz here. We could take these two channels here and bond them together to get a single 40 megahertz here. That means we are doubling the frequency that we have available to us. And, at least theoretically, also thereby getting double the available bandwidth and data throughput by going to that next range. And then you can also even bond the 40 megahertz space, so we'd have two of these 40 megahertz ones and combine that down into this 80. Now, you might see these bonded into 40s and 80s. Haven't really seen this one yet. Might be out there somewhere where you kind of, grab the whole pie. But certainly 40 and 80 is common. You don't need to know that for the CompTIA IT fundamentals. I'm just kind of getting a little bit of extra information here for you. For IT fundamentals, mainly I just want you to know that 5 gigahertz usually gives you higher bandwidth, more data throughput, and it has a shorter range. And in an upcoming whiteboard, upcoming slide here, you'll need to know which standards will use the 5 gigahertz range. Also, I can't remember which ones. It might be these red ones in here. Somewhere in here, there's also these channels that overlap with certain weather equipment, so there is a possibility that you could get an overlap there. I don't know if it would be the weather broadcast or something like that that takes place every now and then when you get flash floods or tornadoes. I guess if you're going to have a tornado hit your building, you've got other problems. Of course, the way people are these days, they're more concerned about losing their Wi-Fi signal than they are about getting hit with a tornado. All right, in our next nugget, we're going to be talking about those 802.11 standards. Stick around for that one if you have the time. I hope this has been informative for you, and I'd like to thank you for viewing. All right, so we've taken a look at radio frequencies and radio channels. Really, the radio channels are just a slice out of the radio frequency range that we have available to us. But there's also a wireless standard. They're all 802.11 something, okay? And they've also been rebranded, which I'll talk to you about here in a moment. Let's just go ahead and take a quick look at all of these standards, because you will be seeing these as you work in the network business. Now, the first one, I think this was about 1999. I'll just stick this in here, 1999. I don't remember all the years for all of these. But this was 802.11b. Now, that sounds kind of weird because why wouldn't you start with A? And there's A right there. But why wouldn't you start with that one? This is also known as Wi-Fi 1. That's recently been rebranded to Wi-Fi 1. The Wi-Fi numbers, Wi-Fi 1, 2, 3, 4, 5, 6, is a fairly recent development where we're trying to get, I guess, a little bit simpler in how we describe some of these wireless standards. Anyway, this really came out and was considered first, despite the letter, because of the fact that it became more prevalent early on. Had to do with supply chain issues with the A standard. But the B standard here uses the 2.4 gigahertz band. And the data rate was about 11 megabits per second. Now, as with 802.11b and probably most or all of the rest of these as well, these are all theoretical maximums. You're never going to get exactly at the highest level of the bandwidth. And a big reason for that is because these wireless networks are really big collision domains. Let me explain what I mean by that. And for that, first, let's go back to wired networks, not wireless, wired networks. Early in networking, we had these things. These would be RJ45 jacks in this device. And you might look at that and say, oh yeah, that's a switch, James. No, it isn't. Because switches aren't pink. I'm just kidding. I know. Because this, what I'm intending to show you here is a hub. A hub might look exactly like a switch, but a hub, well, if it has a message that's destined for somebody, let's say that there's a message coming in on this port for whatever IP address is, 10.10.10.5. And let's say that this one over here is .5. Well, on a hub, it just broadcasts that message out of each channel, and 5 will pay attention to it, and everybody else will ignore it. But it's very, very noisy in terms of the network traffic. There's a lot of overhead and a lot of waste. Now, if I redraw this and just relabel this to a switch, remember that a switch will come in on a certain port. There's the destined traffic 4.5. But because the switch has memorized the specific MAC address of the device that's plugged in right here, it will not broadcast that same message out of all these other channels. Instead, it directly sends it right over here to that port. So why am I talking to you about these kinds of hardware devices when I'm talking about wireless? Because you just saw the disadvantage of a hub, right? Well, what happens here when you have a wireless communication is that you've got this, this Wi-Fi access point right here, and it's sending out its data. Well, there's no way to really isolate that on a single direct message to only one client right here. All other hosts that are on the network kind of also see it like a hub, but they just will ignore it if the message is not destined for them. So that's one reason why the speeds that you see on wireless, this is a theoretical maximum. If you were, on the moon and there were no other interference in between your laptop, let's say, and the access point, and there were no collisions with any other network devices, then yeah, you'd probably get 11 megabits per second. And same is true of all the rest of the speeds that I'll show you. Now then, as we move on, however, we move on from Wi-Fi 1 or 802.11b to 802.11a. Also, for the IT fundamentals test, if you're planning to take the test, they're not concerned with the Wi-Fi 1, 2, 3, 4, 5, 6. They want this 802.11 designation that we see all the way through here. I'm just telling you the Wi-Fi numbers there because that's more current. But with 802.11a, that moved into the 5 gigahertz space, and you can see here it gave us 54 megabits per second. But we just didn't see it implemented all that much, even though for most purposes it was actually better. So wanting to stay within the 2.4 gigahertz range, they moved on to 802.11g, now known as Wi-Fi 3. This also matched the speed of 5.4 megabits per second, and it also gave us but it still used that 2.4 gigahertz range. Now, because of compatibility issues, there was starting to be some problems here because we had some, laptops, let's say, that had an 802.11a card and some had an 802.11b card. One was 2.4 gigahertz, one was 5 gigahertz, and we had some problems there with the compatibility. So what they did was they came up with this 802.11n, and that is capable and compatible with both ranges, 2.4 and 5 gigahertz. The other interesting thing about N is it was capable of working with bonded channels or single channels. So in a single channel, this would be like 2.4 gigahertz, for example. It had a speed of 72.2 theoretical maximum. And that's actually pretty respectable. But remember in our last nugget, I showed you that in the 5 gigahertz space, you can actually bond two channels together and effectively get twice the throughput because you're getting twice the megahertz out of it. So using bonded channels, notice that we're getting just about double 72.2, and we're getting about 150 megabits per second. And then also within the 802.11n, they figured out a way to do multiple input and multiple output. This means that, let's just say that I've got this wireless access point here, and over here is my laptop using wireless. Now instead of having just a single message transmitted back or forth between these two, it can have open, multiple channels, so to speak, thereby being able to send more data in parallel and have a higher throughput of data between the two devices. That's what MIMO is. Multiple input, multiple output. Sometimes I've heard people call it MIMO. So MIMO, MIMO, potato, potato. And then moving past that, we went into the 802.11ac. Now we're starting to get into pretty modern network equipment. This is, at the time of this recording, this is probably one that you'll see the most in terms of those that are more up to date. That's Wi-Fi 5. It's also in the 5 gigahertz range. Look at this, 1.7 gigabits per second. Why? Because we're using MIMO, or MIMO, and we're using multi-user MIMO. You see, this situation over here that I showed you a moment ago, that's only capable of doing MIMO between one host and the access point. Then we have to take turns with someone else's laptop here. Then they can do, MIMO between the 2 points. We cannot do both of these at the same time. Well, this allows for multi-user MIMO, and therefore we're able to do both at the same time, and thereby also increase our throughput dramatically. And just for giggles, I thought I'd show you a photo of one here. I've gone to Asus website right here, as you can see up at the top. And if you go into their networking section, you can look at their Wi-Fi routers. This is an 802.11ax. We'll come up on that one next. But the main point I want to show you here is it's a MU MIMO. And look how many antennas it's got on there. I don't know, man. That either looks like Stonehenge or the alien mothership. Or maybe there's a relationship between the two. Did you think about that? Anyway, because of all of these antennas, it's able to support multiple channels of communication simultaneously with multiple users at a time. By the way, it looks like this multi-user MIMO is only on 1.7. It actually applies to both of these. I just didn't have a way to put it smack in the middle. But here you can see another standard goes up to 3.5. And then, like that access point that I just showed you, that was actually on the 802.11ax standard, which at the time of this recording is very new, and that's Wi-Fi 6. That operates in the 6 gigahertz range. This whole last section right here is not part of the IT fundamentals exam, just so you know, because it's too new. It just came out. This is capable of up to 9.6 gigabits per second. Now, I do also have to point out, at a certain speed, this really becomes irrelevant. What do I mean by that? Well, let's say that this access point right here is, Wi-Fi 6. And we're capable of putting out 9.6 gigabits per second, but on the internet here, our ISP only has a connection here to our access point of 1 gigabit per second, okay? So it kind of doesn't matter. If we're talking about only internet access, then I can only get 1 gigabit per second anyway. Even though this has a theoretical maximum of this speed here, the internet cannot go any faster than what it's getting from my ISP up here. Now, one place that I could get higher speed and enjoy it here with Wi-Fi 6 would be if I was transferring data from this laptop here to this laptop. Then between these two hosts, I would be able to enjoy the full internal access of that Wi-Fi 6 access point. So those are your wireless standards in the 802.11, which have now been rebranded to the Wi-Fi followed by a number. I hope this has been informative for you, and I'd like to thank you for viewing. Okay, so I thought I would go ahead and buy a wireless access point for you so you can kind of see how the configuration goes. This is one that I've never worked with before. I haven't worked with this brand before, so we'll explore it together, but I still feel confident going through it because most of them are the same. The UI is going to be a little bit different, but they're otherwise mostly the same. And I was going to show you the box, but since I use a green screen, it kind of disappears like that. Oh my goodness. But here's the actual device. It's a TP-Link. What does it say? AC1200, and here's the antenna that you would then, point in different directions. You generally want to point this towards where you expect most of your clients to be. So that's what you'd do with these. But anyway, these giant antennas on here. This is a MU MIMO. When we talked about that in our last nugget, you can see on the back of that I think I'm covering up with my microphone. You can see on the back of this there's 4 ports. The yellow ones there, those are going to be for my my Ethernet LAN connections, and the blue one is the WAN connection, which would be the internet. All right, now I've gone to the web page for this device. Now, how did I get there? What happens here is these devices, most of them, are also DHCP servers. So it will issue an IP address to network cards that are requesting an IP address. I installed a new network card, and I plugged the Ethernet cable into one of those yellow ports that I showed you earlier, and then I plugged the other end into my own Ethernet card attached to my computer. It's on a USB port. It's USB adapted Ethernet card. And then in the instructions, it tells me what the IP address is. Normally, it's going to be this. For most access points, it might also be 192.168.1.1 or 192.168.0.100 I've seen as well. But usually, it's 168.0.1. Okay, so now that I'm here, it's giving me the opportunity to enter in a password. This is a password that will be used to administer this device in the future, and the importance of it is if I enter in something that's easy to guess and a hacker or some curious neighbor or somebody like that figures it out, then they can control my access point, which could be a severe security issue. So here I'm going to enter in a password, and I can go ahead and click on the little eyeball button here to see what the password is. You can see it's not very secure, okay? And this reason for that is because I just bought this from Amazon, and I'm probably just going to return it. I only bought it for purposes of this demonstration. I feel kind of bad for doing that, but people, I'm willing to violate my conscience for your sake, okay? So I just hope you are aware of this. Anyway, so now we're going to go ahead and click Let's Get Started. And some of these things not related to networking, I'm just going to very quickly go through real quick. I'm in, not Chihuahua, I'm in Arizona. I can set up a static IP address, but I'm going to choose a dynamic here. Oh, by the way, before I forget, do also notice that down here, There's a QR code that you can scan with your phone, and the usefulness of that is that you can administer this from your phone. I'm going to go ahead and close that for the time being because it's covering up the next button. Remember we talked about MAC addresses in a previous nugget. Some ISPs will only bind to a specific MAC address. That's not going to be the case in my case, and I don't think that happens very often. Maybe I'm wrong. I'm going to say do not clone the MAC address. If that went past you, don't worry about it. We're going to get onto the wireless stuff, which is what's most important for our purposes. And that pretty much starts here. Let me press Control Plus on my keyboard to zoom in more to make all this a little bit more visible. That just magnifies what we can see. Here I want to enable the wireless radio. I could clear that, and if I did that, this would really just become a 4-port switch. Doesn't have a lot of usefulness for me because it's kind of expensive for a 4-port switch, but I could clear that if I wanted to. But I will leave this enabled because we want Wi-Fi, don't we? And then this is the SSID. The SSID is the Service Set Identifier, and this will be whatever we want people to see when they are searching for Wi-Fi signals. And then this is the password that they would have to enter in order to be able to get onto my Wi-Fi. In this case, just a bunch of numbers. I'm just going to call it instead something different, Fly Wi-Fi. How about that? So you can change this to whatever you want. Now notice that I can also hide the SSID. This means that when people are scanning for a Wi-Fi, whether they're using their phone, their tablet, their computer, whatever it is, they won't see this at all. And in order to connect to it, they have to make a manual connection. They would have to type in TP-link and then the number that you see there and everything. So they would have to type all this in manually in order to make the connection. Sometimes that's useful. It's a little bit of a rudimentary security measure because especially if you're in a densely populated apartment complex, for example, you don't want a bunch of freeloaders. There are people that are smart enough and use hackers' tools and they can figure out what your password is, and we just don't want them on my Wi-Fi at all. I don't want them to be able to see it. So it's kind of security by obscurity is what we call that. We will leave ours visible because most of the time you're probably going to want to do that. Oops, I guess I need more passwords there. Fly Wi-Fi 99, how about that? Okay, then we get a nice little summary. And if that's what we want, we would then click on Save. Now, while this is saving, I'll point out this is a cheap little Wi-Fi access point. I think it cost me $39 maybe. The one I showed you in our last nugget, the one that looked like Stonehenge or whatever, the mothership, that one was almost $500 for that 802.11ax device, the Wi-Fi 6 one. Now, once it's set up, I have clicked over here onto the Basic tab. And this may show you what the connections are, just to give you kind of a visual. Notice that we are on the 2.4 and 5 gigahertz ranges here. Mesh devices, FYI, are just a way of extending your wireless reach so that if you have a dead spot in your house, you can add an additional device over there to extend the range. Basically what they do is it's just another Wi-Fi, really, is another access point, and it just receives signals from your access point and then repeats them further on to another part of your house or business. I'm not going to elaborate too much on some of the rest of these things, but you can see that we have an internet connection here. We talked about that a little bit earlier. There is the possibility to set up a guest network right here. I don't know if this one does it, but some of them will allow you to throttle them. So, not to throttle the guest, but to throttle the internet connection. Anyway, so, for example, I've got a gigabit E, but I use my network for business, and I really need it to be as fast as possible. So if I have a guest come over, maybe I want to limit them to 10 megabits per second. I could do that. I don't think this one allows that, like I said, but otherwise you can specify kind of a throttled bandwidth here if you want. And then I would enable the guest network, and it would show up a different guest ID here, and you can again call that whatever you want to. I mentioned earlier in a previous nugget there are also parental controls, which will take your teenagers usually about 2 or 3 minutes to get around, but you might as well add them in if you can. Now, for our purposes, I'm going to go to the Advanced tab because that's going to have more of the things that we discussed earlier. Notice that on the 2.4 gigahertz, we have 802.11b, G, and N. Remember, the N kind of combines both 2.4 and 5. This one's very convenient for us because it's giving us an automatic channel width. What these will often do is when you first boot them up, they will look at the rest of the Wi-Fi signals that are within its reach, and it'll see what's already in use. And if it sees a certain channel that it would have used, but it's already busy with some other channel, or that there's too much overlap, like we talked about in a previous nugget, then it will choose another channel that's not being used or doesn't have as much of a risk of overlap. In this case, it chose to give me channel 2. If I go over to the 5G side of things, we can see that it also did an automatic scan here, and it gave me channel, I think that's supposed to be 161, but since I zoomed in, I think it word wrapped or something. Nope. I think it is 161 though. It just kind of wraps around. And in a similar fashion, I could do similar kinds of settings here for my guest network, but I have not yet enabled that here. Now let's discuss here. I've gone to the wireless section, and then I clicked on wireless settings here. And then we have some selections here to make under the WPA section that we see right here. This is going to be useful if I'm in a personal environment, like a small office, home office. I'd choose WPA2 or WPA3. That's kind of an emerging standard. It's very secure, and it's beyond the scope of the IT fundamentals, but I'll come back to that here in a moment. Basically, the idea is if you just leave this at automatic, it'll switch over to WPA3 when possible. And then there's WPA2 Enterprise. With this one, what you would do is you would actually have a server somewhere that handles all of the authentication. It's well beyond our scope here. But just so you know, you would point it to the IP address of a server that uses a specific port number. This is the default port of 1812. And you would enter in a password so that you would not have an imposter trying to become your Radius server instead to handle authentication, and then it would try to collect credentials from your devices. But we don't do that, okay? This is well beyond our scope for our purposes. So we'll stick with this one for now because it's probably the most prevalent. The most secure way to do this would be to do WPA2. WPA is okay as well, but WPA2 is more secure, and you can choose which kind of encryption you want on the password. TKIP is no longer considered secure, and especially if you're using 802.11n, TKIP does not work well with that, and it could cause some problems. So we'll choose AES. Now, this password will then be secured by Advanced Encryption Standard when you use all of these settings. Now, this one does offer the ability to change the transmit power. Remember, they default to high because these manufacturers want everyone to see that they've got the strongest signal in the neighborhood. Everybody would want a TP-Link Wi-Fi router, with our Wi-Fi strength being so strong. But if it caused problems with a neighbor, especially in a dense apartment complex, for example, or something like that, you could switch it down to middle or even low. And you might only need low if you're in a smaller apartment. And I think that's pretty much all we have here. Oh, the Smart Connect, I think I might have misidentified that earlier if we talked about it. What this does is it allows you to have the device automatically negotiate the best wireless band to use depending upon usage. But here we can also do WPS. This is what I was thinking of earlier, actually. This is a one-method push button, so you can click Start WPS by clicking there, and then it would automatically pair with a destination device for you without you having to enter in the password. All right, now the TP-Link Wi-Fi router did not really show an option to change the channel, so I've just gone to my own access point here, and notice that I've cleared out the SSIDs and the passwords for obvious reasons, but on the 2.4 gigahertz range for B, G, and N, we see that it has auto right here. Remember that for the 2.4 gigahertz range, it's best if you choose channel 1 for the first access point, then channel 6, which is 5 channels away, for the second one, and then channel 11 for the third one. I've only got one in my environment, so it almost really wouldn't matter which one I selected, unless I had a neighbor that was causing collisions because we were on the same channel or channels that were too close together. And then moving down to the 5 gigahertz range for AN and AC, we have two separate ones here. I've got a 5 gigahertz on one SSID that I could be using. I've only got a few options there, but that's okay. Those are all good options. And then on the second one down here, this is where I have the higher channels that are available. And again, you sometimes have to just coordinate that with neighbors or other access points that might also be using similar channels. The basic idea here is you just don't want to step on another channel that's already in use. All right, so that's where I'm going to stop here. There are a lot of other good features on this TP-Link device. I'm kind of surprised because it was so inexpensive. I didn't think it would have as much as it does. But that's all we have time for now. And that's more than you need to know for the IT Fundamentals course and the exam. All right, I got a Amazon return to make, so I got to get going. I hope this has been informative for you, and I'd like to thank you for viewing. All right, folks. First question I have for you today here in this pop quiz is, why am I dressed up? Well, it's not because today's a pop quiz. It's because my son's going to get married in about an hour and a half, I guess. So before I go to the wedding, I thought I'd go ahead and get this video started, all right? All right, so for the first question here, which of the following is the most secure password for an AP? And as usual, with these questions, I'm going to normally pause for a moment and give you about maybe 3 seconds if you aren't able to hit the pause button on your player in time, just in case. And then I'll resume and we will answer the question. Okay, so for this one, it occurs to me that when we were working with the TP-Link access point in the demonstration that I had, they didn't even have this option that I could remember. This means no password, okay? So that doesn't seem very much like a good option. They didn't even have the WEP, which is Wired Equivalency Protocol, and that one was not visible there either. So this question may not be completely fair because these two options were not even in the stuff that I could show you. However, neither one of these are secure. Wired Equivalency Protocol used a rudimentary encryption, but it was very poor and easy to crack. Open is just no password, so obviously there's no security there. Wi-Fi protected access is better, but Wi-Fi protected access 2 is the best one that we have in terms of the IT fundamentals. But do remember, there's an emerging Wi-Fi protected access 3, which will be even better. But for this is your answer. All right, pop quiz question number 2. Your wireless clients use wireless network cards in the 2.4 gigahertz frequency. You need to configure the 3 access points to cover your site. Which of the following channel combinations are usable? All right, so remember, we have basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then there's also a 14 out here, but you don't always see it. And remember, we also need 5 channels of separation. If we need, where do I have it here? If we have 3 access points that we need to configure, the only way even mathematically to have 3 of these available and to have 5 channels of separation between them, the only way you can do that is not 2, 6, 8, because 2, 6, 1, 2, 3, that's only 4 away, and then 8 is only 2 away, so that won't work. 14 and 11 are only 3 away, so that won't work. This one right here. 1, 6, and 11. Look at that one. 1, and then 5 hops away, 6, 5 hops away, 11. So that is your answer, and obviously this one's just patently wrong. And it's not really part of the IT fundamentals exam, but let me explain to you why you wouldn't want to have all the access points using the same number. If I have access point here, and here, and here, let's just say that they're all using channel 1, and then I've got a client right here, which is represented by this circle, and they're connected here because they're closest to it, they get a good signal from it and everything. But as they move over, maybe they're slightly closer to this one, maybe they move to the conference room, well, these will all have the same SSID, but if they also have the same channel number, then these things get confused. They aren't really sure which one of these to connect to, and it's just causes a real problem here. So that's why you have these on separate numbers, like a number 6 right here. So as it moves closer over here, it'll also switch channels and then connect to that one instead. Which of the following are best practices? All right, so let's take a look at these. First one here is change the default SSID. Now that would be according to the IT fundamentals best practices. You don't have to. You saw in our TP-Link, it had, I can't remember how it was called, but it was TP-something to designate it as a TP-Link. One of the reasons why we want to change that default SSID is because there are certain SSIDs that have a default password. You can actually Google for this. So if you look up a certain brand and no one bothered to change the password for that SSID, the administrator password, well then just anybody could connect to it and manage it and vandalize it or something like that. So that wasn't really particularly in the demonstration either, but it wasn't as relevant on that TP-Link one because it forces you to change the default password anyway. But anyway, this is a best practice from IT fundamentals. And then change the default frequency? No, not necessarily. You might need the frequency. Change the default country? Why? Okay. Change the default time zone? Possibly, depending on if it's already correct or not. But that's not really a definite best practice. But change the default password for sure is. So, at least according to IT fundamentals, A is one you should do, and E is the other correct answer. All right, which of the following would interfere with a wireless signal? All right, let's take a look at this. I think I described all of the ones that would interfere in the materials when we were looking through these. Glass, even though we can see through it and it looks like it wouldn't interfere with anything, it actually does. Especially if you have those walls that are big glass blocks. Those might be more of an issue there. Walls, any kind of a wall, drywall with studs, bricks, any kind of masonry, stucco, all that kind of stuff could interfere. Microwave ovens, remember, a lot of times those are on the same frequency as your 2.4 gigahertz range, so is a cordless telephone. So all of these things up above here are orbiting satellites. I'm not quite so sure that would have anything to do with this, so we'll go with the top 4 options there, A, B, C, and D. All right, so there you have it with your pop quiz questions. Admittedly, I did a little bit of teaching as I was going along with some of those. Hopefully that was still useful for you. I got a wedding to get to, so I gotta go. I hope this has been informative for you, and I'd like to thank you for viewing.